Hello everyone, my name is Faraz Awan and I'm a data scientist at Urban Big Data Center UK. I'll be presenting my work on leveraging mobile phone app data for urban mobility analysis, particularly focusing on challenges and insights in travel mode detection. So, when it comes to urban mobility and transportation planning, people's transport mode choices can provide significant insights to policymakers. For instance, it can play a really important role in the decision-making process for infrastructural planning by providing data and information. Conventionally, survey-based approaches are used to collect these data and information that come with their own challenges and limitations. For example, looking for the volunteers to participate in surveys and inevitable human error while filling out those surveys. However, these challenges and issues associated with these conventional methods could be dealt by using comparatively modern and more popular data sets such as mobile phone app data. These data sets are spatially more detailed and accurate. However, there's a need of understanding the potential issues and the challenges associated with travel mode detections of the trips detected from mobile phone app data. Some of the major objectives of this study is to examine the issues and the considerations in leveraging mobile phone app datasets for travel mode detection. Moreover, evaluating the reliability of the travel mode analysis based on mobile phone app data. Furthermore, we would also be talking about the limitations and the shortcomings of detecting travel mode from mobile phone app data. This study focuses on Glasgow City region and fundamentally uses two data sets. Our primary data set from Hawk Industries. It is mobile phone app geospatial data, and it contained the data of around 64,000 users, and there were around 6.7 million trips detected from this geospatial data. Some of the key attributes in this dataset include de-identified user ID, GPS points generated by different apps installed in the smartphones of the users, and for each GPS point, respective timestamp. On the other side, our Scandi dataset was acquired from Travel AI, and there were around 363 users in that data set, and it contained around 1.13 million trips carried out by those 363 users. Some of the major attributes in this data set were, again, de-identified user ID, trip ID, GPS points, trip GPS point generated during uh, all those trips, and against each GPS point timestamp, and the travel mode that was used in order to make any particular trip. Let me tell you that our primary data set, that is mobile phone app dataset, was used to detect the trips, while the dataset acquired from Travel AI, that is our Scandi dataset, was used to train machine learning model and then apply those machine learning model to the trips detected from our mobile phone app data. Our methodology, as I already have explained, consists of three steps: detecting the trips from mobile phone app geospatial data, training machine learning model on secondary data source, and then applying the trained machine learning model on the trips detected from mobile phone app data. As far as detecting trip from the geospatial mobile phone geospatial data is concerned, it's out of the scope of this work. However, in order to explain the limitations and the shortcomings with detecting the travel mode of the trips detected from mobile phone app data is concerned, it is important to explain the trip detection process. The trip detection process consists of four steps. First, removing the GPS points with low precision. Second, removing inaccurate GPS points. A GPS point is labeled as inaccurate if the speed between the current GPS point and the previous GPS point exceeds certain thresholds. Uh, Moving forward, we detect the stay location. Stay location process would be explained in detail in next slide. And once the stay locations are detected, trips are formed between stay locations. In order to understand the stay location detection process, consider the following GPS points generated by different apps installed in the smartphone of some user A. These GPS points were generated in particular time interval. So we choose the first GPS point and encircle all the neighboring GPS point within 500-meter radius. And then using the timestamp of the last GPS point within that GPS cluster, we check if that particular user stayed in that location for at least 5 minutes. If yes, that particular cluster area, that location is labeled as stay location. Starting from the first point outside the detected location, we keep going on looking for more stay locations. Once all the stay locations are detected, flow is generated. Flow is established between consecutive stay location, which is known as trip. Here you can see the overall and aerial view of the methodology. In the bottom, the trip detection process that I just explained is provided. Above that, you can see the machine learning training process. Two tree-based machine learning model, decision tree and random forest, were trained on several features derived from our secondary data set from Travel AI. Those features, those attributes include average and 95th percentile of speed and acceleration. Day attribute, it basically indicates if the particular trip was carried out during weekend or weekdays. Temporal attributes, it again indicates which time of the day particular trip was carried out. It has four possible values: morning, afternoon, evening, and night. Moreover, angular deviation was also used as one of the attributes. It's one of the important attributes because it deals with the route characteristics. The route particular trip was carried on. It indicates the straightness of the route that was used to carry, to make any particular trips. Why it is important? For example, consider any trip carried on through train, subway, bus, or even car. You will find those routes comparatively more straight as compared to any other trip carried on through active travel mode, for example, car and bicycle or walking. Moving forward, we also use OT points attribute. This is basically a flag variable which indicates if a particular trip started and or ended somewhere near bus station, railway station, or service stations. Following the convention, secondary data set was divided into training and testing data. 67% of the data was used for training and 33% of the data was used for testing. When it comes about travel mode detection in literature, rule-based models have been found quite effective in the and quite simpler. So for the sake of comparison, we also applied rule-based model on our trip data set, those trips detected from mobile phone app data, in order to see how effective a rule-based model could be uh, for detecting the trips uh, from mobile phone app data. Looking in the results, you can see that our machine learning based models perform really good with 91.5% accuracy for random forest and 90.9% accuracy for decision tree. In contrast, rule-based model uh, showed significantly low accuracy, which was 34.8%. For further evaluation, using the same configuration, we retrained our machine learning model, but this time we merged certain classes. For example, walk and bike categories were merged into single category called active travel, and bus and train were merged into single category called public transport, to see if mergings of these classes can improve the performance of model. However, when you look into the results, you don't see any significant improvement. Random forests observe around 1% accuracy, whereas in case of decision tree, that improvement was even less than 1%. Given their good performance on the testing data, these models were applied on the trips detected from mobile phone app data, as our primary trip data set didn't contain any ground truth. So manual validation was carried out based on the route and spatial characteristics. Overall, models showed similar performance. However, for further evaluation, we compared the statistics generated from our primary trip data with that of Scottish Household Survey, and we notice difference between the stats. For example, if you look into the trips, of all the trips detected from mobile phone app data in 2019, 71% of the trips were car trips. However, in contrast, its Scottish Household Survey, around 50% of the trips were car trips in 2019. So why this biasness? Why uh, these difference in percentages? In order to explain this, I'll take you back to trip detection part again. Consider the following scenario. A trip was carried out between origin and destination, and you can see the intermediate GPS points generated during this particular trip. These intermediate GPS points are very important because some of the attributes such as uh, speed, acceleration, uh, and angular deviation that were used to train our machine learning models could be calculated if these intermediate GPS points are available. If any particular trip doesn't have these intermediate GPS point available, our machine learning model cannot be applied on those trips. Now, the question is, why these intermediate uh, points won't be available? In order to understand that, consider the following scenario. You are traveling in subway or in train, and your train enters in the tunnel where you don't have GPS points. You don't have GPS signals. You will end up having a trip without intermediate GPS points. And when we conducted the analysis, we found out that around 20% of the trips, only 20% of the trips contained intermediate GPS points, whereas 80% of the trips had missing intermediate points. So technically, majority of the trips identified as the car trips by our machine learning models were actually the car trips, but because of the absence and the underrepresentations of non-car uh, trips, there was higher percentage of car trips. So In conclusion, uh, machine learning models outperform rule-based models. However, missing intermediate points can be threat to validity to analysis, which is caused by the underrepresentation of non-car travel modes. Hence, there's a need for potential novel solution to address data bias and travel mode detection from mobile phone app data.